unfortunately for you. So thank you for the invitation, and thank you all for coming. So first, I would like to say that it's a joint work with collaborators from Grec Lab, and especially from the work of Ryan Webster, which is in postdoc at our lab. So in this talk, I will talk about detecting overfitting in generative models using latent recovery. So that's a lot of keywords, so I will have different steps to explain it. So first, let me recall the context. So as you all know, deep learning now is a very powerful framework to do a lot of things in signal processing or computer vision. And especially for imaging, convolutional neural networks now gives state-of-the-art performance in many applications. Most successful one were, let's say a few years ago, classification networks like VGG or inception networks. But in this talk, we are not speaking about image classification, that is, for a given image, trying to infer what is the semantics, is it a cat or a dog? We try to do the opposite. We try to generate images. So what is image generation? The rough idea is that you give me a data set of image you would like to samples, and we will train a convolutional network to do so. So this is unsupervised training. During this training, we'll try to generate samples that looks like examples from the training dataset. And when I say looks like, it means perceptually or semantically, it is similar. So there is a great underlying question of how do we compare images, right? And what I would like first to underline is that if training can take days or weeks, synthesis is very fast. On the GPU, it takes only a few milliseconds, and even on CPU, it takes seconds, right? Using those kind of architecture. So we'll mostly focus on one architecture, it's not the only one, which is called GAN, Generative Adversarial Networks, which has been proposed just a few years ago by Jan Goodfellow and collaborators. And a few weeks ago, he shares this tweet in which he shows what we obtain each year since GAN have been proposed. And as you can see, for phase generation, now we are very close to photorealism. So if we look into more details, so I will start with DCGAN, which comes from 2016 by Redford. It used a large number of images, a third of a billion, to generate faces, and already 3 years ago we had very good results, and mostly because those images were registered. We use computer vision system to register faces, and the system managed to generate reasonable faces. For some reason, people like a lot bedrooms. I don't know why, but they have this kind of result, which is not as good because it's not registered, right? And for other ImageNet categories, we don't even know what it is. You can guess maybe that here it's a dolphin or this is a plane, I don't know. But it was not that good. But just 2 years after, results are really impressive. So for faces, it's even better. Now we have full AG images of fake celebrities, or supposedly so. And it works for other image categories. So bedrooms again, but other categories like bikes or horses. So there are still a few glitches. For instance, we have a horse with 2 heads here, but otherwise it sounds quite good. For instance, this bike is really impressive. And it's not over yet. Just this year, 2 new methods have been proposed. So one is called PG-GAN. We'll see why in a few minutes, but you can already guess. It's on a very large data set. And it gives very impressive results as well, okay? To the point where it says, okay, generating dog is easy, right? Just texture with a bunch of eyes, okay? For the following work of Karas is called StyGAN, just for faces. So the dataset is not that big compared to the previous one, but still, it gets really amazing results. Those are, of course, quite cherry-picked. Those are the best to generate. You can visit this website if you want. There are many of those who are artifacts, but for those, you can barely see if those are fake. So the motivation of this work is that the paradigm from the last few years is we have very good generative architecture, very good generative models, and the paradigm is that you just take the bigger is the better. Okay? And bigger means you have deeper networks, wider networks, and of course, larger data sets. And because you have larger data sets, you have very strong suspicion that actually the generative model is just copying the data. Okay? We have no way to, when we have billions of images, there are no way to decide if this is a copy or not. Okay? And the problem is that this suspicion is supported by some evidence already in the literature. So if I go back to classification networks, recently few works have shown that those networks, which are very similar to generative networks, are memorizing. So Zheng, for instance, in this paper, 2017, just took out of the shelf very good classification networks that perform very well and did simple experiments like randomize the labels. So this cat is now a dog, this other cat is now, I don't know, a boat, and still, for a training data set, it works perfectly fine. Of course, for validation test, for other image that he never seen, the networks perform like a random guess. But otherwise, it performs very well, so it shows, it demonstrates that the network is memorizing. And even worse, if you take random images, it still does the same. Okay, that is a big problem. And independently, some people have shown, for instance, Shrocky, the same year, that if you give me a classification data set, it kind of overfit the data so that I can do successful membership attack. It means that if I take an image, I can compute the probability that this image has been used during training. Okay, that's raised a lot of problems regarding privacy. So we are considering generative networks now, so we could say, okay, this is a different story, right? There is few papers about that, and one interesting is the one of Alidas Newsom, which demonstrated last year that if we train a specific network, which is called autoencoder, to generate images of disks, you can even prove that actually the autoencoder will learn a template model that tries to mimic the disk you have seen during training. So this is good news. It shows, for that experiment at least, that we are not overfitting the data. But in the meantime, they also show that those kind of architecture fails to generalize. And for classification network, generalization, we'll see in a minute, is the kind of opposite of overfitting. So still they have suspicion, right? And quite recently, some people for GANs, so we'll look at the technical details later, but in GANs we have a classification networks, and people have reported that this network memorized the training set. While in theory you should not doing so, but this is a practical problem. So the problem I would like to address in this talk is the following one. I would like to assess the quality of generative networks, but regarding the problem of memorization, of overfitting. Okay. So just to give you an idea, this is two pictures from a training data set, and this is the image I get training a DC, a Wasserstein GAN, or a progressive Göring of GAN. So those images are very close. So can we say, is that overfitting, or is it just that the data, we have so much pictures of Eiffel Towers in the data set that it's normal that the generator generates this specific picture. And a related problem that we'll maybe investigate in the end is, what about privacy? Okay, so let me first give you a short overview about generative networks. So roughly speaking, most generative models are using the same architecture, which is this one. Typically, it's the fully convolutional network that we feed with latent codes. This is a small dimensional vector that are often random. By low dimensional, I mean that they have about 100 of entries. This latent code is multiplied by the big matrix, is mapped to a higher dimensional space, and reshaped into a small 4x4 pixel images. But this image has a lot of layers, right? A lot of channels. And then progressively, we are increasing the spatial resolution of this image, reducing the number of channels, using convolution blocks that are strided to upsample the resolution. So, and we continue that until we reach the desired resolution. So in DC GAN, they stopped at 64 or 128, but in last networks, we can go until 4K. So if all those methods use the same architecture, they completely differ on the way they train this generator. So the list here is not exhaustive. I will just investigate the one in blue, so most of them, actually. But I will just explain in detail the third 3 to 1. Okay. So let's start with autoencoder, which has been around in the literature for many years, now 30 years mostly. So the idea is quite simple. We have a generator that we would like to train. And the problem is that we want this generator to generate images, like digits, for instance, from this, with random code that we don't know nothing about. So the simple idea is that we will have a second kind of a mirror network that will take images from the dataset to encode latent code that will feed to the generator. And then for training, we ask that the output is as close as possible to the input. And like usual, we use the Euclidean distance, and we squared it to make it even better. And that's it. So you may have guessed that there is a problem. When training is over, we still don't know how to sample Z. So a variant to do that is variational autoencoder, in which Z is randomly, during training, sampled from a given PDF, typically a Gaussian distribution, which is parameterized by the encoder. Okay, so this gives quite interesting results. But quite recently, people have, so it's Boshanovsky, have done the following thing. Instead of trying an encoder that we maybe get rid of, directly we try to train the generator and the latent codes. So the problem looks like this. It seems even simpler. We train the generator to provide images that are very close to the images from the dataset, but for a given input code. So we are just trying to define a mapping function between latent code and generated images. And this gives very good performance, surprisingly. Last but not least, the best method on the market right now is GANs. So what are GANs about? This is actually a very good, elegant solution to the following problem. In previous method, we have to define a metric between images, which is a very difficult problem. So the solution of Goodfellow and collaborators is actually, again, like autoencoder, to use a new conversion network, which this time decide if a generated image is fake or not. So this discriminator is trained to recognize, to differentiate between training example and fake images. So we don't have to define a metric between those images. So the optimization problem looks like this. If we just forget about G, G is fixed, we just want this discriminator to generate 1. We maximize this function to generate 1 if an image is real, and 0 if this image is generated. And actually, the generator is trained to fool the discriminator. So both in theory and mostly in practice, the discriminator, in the end, is not able, supposedly, to discriminate between generated and trained image. Okay, so we have many different architectures, many different models for generating images. How do we evaluate them then? Because don't forget, we don't have a metric between images, right? So let me first give a quote from the deep learning book of Goodfellow and al. That concludes the full book by the following sentence. The most important thing is to improve generative models, but as well, designing new techniques to evaluate them. Okay, so this is exactly what this talk is about. So in theory, it's pretty straightforward. We have a data set, we have generated images, we should compare the distribution of the two. Problem is that we don't know the distribution of images. We only have few samples, and don't forget that those images live in very high dimensional space. So even estimating the distribution is difficult. And even if we manage to do so, we still have to define a metric between images. So this is a very difficult problem, for which the state-of-the-art method at the moment is the following one. It is called the Frechet inception distance. Basically, what it does is to first reduce the dimension of images by passing through conversion network. So it's inception network. It could be VGG if you like more this one. Okay. So instead of having millions of pixels, we have now thousands of vectors. We aggregate them for each data set, generating the set and data set. And to compare the two, we fit a multivariate Gaussian distribution. And to compare those Gaussian distributions, we compute the Frechet distance. And the Frechet distance is no more than optimal transport between two Gaussian distributions. Okay, so we'll keep that in mind. We'll compare this metric later. Okay, so now what about memorization and overfitting? We first have to give a definition. So for classification networks, it has been well studied, and it can be stated as follows. Generalization is when a network performs as well on training data or on data that it doesn't have seen. So for this specific problem, we split generally the data set into a training set and a test set or a validation test. I will say the two are the same for me. Okay, so we compare the performance. If the performance are the same, we said the network is generalizing. And if it doesn't happen, we say it overfits. So overfitting is just the discrepancy between performance on training and test sets. That's it. And memorization is the more extreme case where we perform perfectly on training set, but not on test set. It's what Zheng did with random labels. So it said classification networks are memorizing. So what about generative networks now? Actually, people are using this term, memorization or overfitting, but as far as I know, I never found any definition of it. Okay? So we'll see how do people do, but the consensus is that memorization is if the generative network is generating image from the training set, and overfitting is when images are very close to the training set. That's the rough idea for now. So how to evaluate that in practice? Mostly, I would say, is by visual inspection. If you look at this PG-GAN from 2016, it says, oh, clearly, the network is not overfitting, it's underfitting because we have these artifacts here and there, and that's it. Recently, what people have been doing is more involved. It's what I'll call nearest neighbor search in a training dataset. We'll see that in a moment. But I must say that some efforts have been done to try to assess overfitting by comparing distributions. Okay? So for instance, this has been done in this work, but unfortunately for very low dimensional images, like NIST images. Okay, so how nearest neighbor search works. So the idea is the following one. We generate a few images, like this dog, and we look at the data set for the nearest neighbor. And we visually assess if those are the same or not. That's it. Okay? So they are minimizing this distance. So like usually, we are using the Euclidean distance. It can be L1 distance, or we can even use features, phi. So phi can be just color pixel values, but it can be VGG features, for instance. And in PG-GAN or PG-GAN, for instance, they show that pictures are not the same. So they conclude that it's not overfitting. The problem is that it's easy to show that this metric doesn't work as you already know. Even for patches, the Euclidean metric is not very good. So for instance, if I take this image from the training set, but I change it a little bit, like changing the background or the color of the air, of course, I will not retrieve the same image. And what is even worse in that CEB dataset, each people is duplicated 10 times with different pose or so on. So we could at least have obtained the same person, but no. If I do just the flip, I flip the image, which is not done during training here. If I flip the image, I get, again, another identity. Okay? And using pixel values or even VGG features, which are much more complicated, it doesn't work. Okay? So what we propose instead is actually almost the same. It looks the same. What we say is, instead of looking for the best image in the dataset, we should do the opposite. For every picture that have been used in the dataset, why? We should look at the best generated image. And it's what we call latent recovery. Okay? So we use exactly the same setting. And surprisingly, it works very well. Okay? So let me give you an example here. So this is the same image I used before. This is what we obtain with nearest neighbor in the training set. And this is what we obtain by optimizing the best generated image, what we call latent recovery. So, of course, those images are not necessarily realistic. Okay, as I said, the pictures were kind of cherry-picked, but still, what is interesting here is that we can see that it's almost the same person, which is flipped, or with different hair color, or with different background. Okay. Now, if I take an image which is not in the training dataset, it's still working quite nice, while the nearest neighbor completely fail. And if I change a little bit this image, like spatial distortion or pooling or stuff like that, I still get an interesting image, while this failed completely. And what was even more surprising for us is that actually if you try to retrieve the code from a generated image, I can do it pretty easily. Okay? So if you compare very closely, the two images are different pixel-wise, because the air are quite different, but we have clearly the same identity. To the point where if I forgot even about the face, just keep the background and the air, I still retrieve the same person. Or if I just take a big patch, I still retrieve almost the same person. Okay. So this is just as a baseline to state that latent recovery is working. So how it happens in practice? Let me first recall that it's a non-convex optimization problem. So we are not assuming that we get a global optimum. Okay, so we are still dependent on the initialization. But for this experiment, we didn't use any restart or anything. And worse than that, we use LBFGS, which is not meant to do that, but that works very nice, for instance, for DC-GAN. So in very few iterations, we get very good results. So it means that we can do this optimization for the full dataset very quickly. So this is for DC-GAN, this is for PG-GAN with larger images. But as I said, okay, it takes longer time, but we can pool actually. If we pool, we can, it accelerates the optimization. So if you are interested, there are a lot of technical details that are given in the preprint. Okay, so what I propose now is to use that as a definition for overfitting. So the idea is to use the same definition that for classification network. That is, we split the dataset into test and train, and see if there is a difference in recovery for those two sets. So the protocol is like this. Divide the dataset into two parts, which was not done in generative network usually. Train on the trained dataset, D, and then compute error for train and test sets. And see if there is a difference in the, let's say, the squared sum of error. So what did we do is to make extensive tests. So we tested very different architecture. So autoencoder and generative latent optimization. Remember that those two generators are meant to memorize a mapping between latent code and images. So supposedly those methods are memorizing. Pure GANs, we took out of the shelves codes that works perfectly fine, that we retrain to follow this split procedure. And we also use hybrid GANs. So what are hybrid GANs? In practice, generating image itself is not a very important application. But for image inpainting, denoising, and stuff like that, what people have been doing is combine GANs with classical encoder and so on, so that we can achieve this kind of application. So those are very important in practice. For instance, there are three different images, three different references with autoencoders and cycle GAN. We tried that on many datasets and for various datasets when that was possible. So first, let me show you some visual experiments. So those are query images that we'd like to reconstruct. So those images are in the train set, these in the validation test set. These are pure GAN methods. So what we can see is that it seems to perform as well on both. This is GLOW, and GLOW is learning mapping. And what we can see is that definitely is very good at reconstructing images from the data set, while it does poorly on a validation test. And for hybrid GAN, here it's a cycle GAN, which is a famous paper. It's still difficult. It seems that it's quite better here, but it's not very clear. So instead, we'll look at histograms. So this is the same experiment, but now instead of doing for 8 images, I do for 4K images. So this is GANs. This is GLOW with different number of images during training, and this is for hybrid GAN, cycle GAN here. So in green, we have the training set, and in red, the test set. So as you can see, more and often, we have a discrepancy between the two, showing that there is overfitting. But quite surprisingly, for the best methods, for GANs, the two histograms seems to be completely the same. Okay? So that will strongly suggest that GANs are not memorizing. But for hybrid GANs, for example, this is a different story. What we can see is that there is clearly a difference between the two. And the more image you use with the same network capability, the less you manage to overfit. As a baseline, we give two different histograms. The yellow is for generated images for which we have kind of a perfect reconstruction. So this is to give you a measure on how we are different from a perfect reconstruction here. And for blue, it's what happens when we distort a little bit the images. So this shows that this is quite good reconstruction, but still not perfect. Okay, so we have made tons of histograms, so I will not show you everything. So instead, we'll grind some numbers. So since histogram looks like, let's say, Gaussians, what we propose is to compare the median value of those histograms. Okay? So it's what we call MRI, median recovery error. And what you can do instead is just simply do hypothesis testing to assess if the two histograms are different or not. So this is done using the p-value of the Kolmogorov-Smirnov test. And as a rule of thumb, we define those two thresholds. If the MRI gap, which is normalized, we compute the median error on the test set, which is always greater than the training set, and we divide it by the error on the train set. So this is between 0 and 1. If this is above 10%, we say there is overfitting. And if the p-value is below 1%, we say, again, we have overfitting. So don't look at all those numbers. Okay, here is the data set. Here are the list of GANs or generative models that we train. And in blue and green, we have values that detect overfitting. And consistently, for every data set, we have the same results. GANs are not overfitting. Hybrid GANs are overfitting when the number of images is not enough. While autoencoder, where is it? No, GLOW is overfitting. And like hybrid GAN, if we use enough images, we are not overfitting anymore. So the question we could say is, okay, GANs are not overfitting, but maybe they are overfitting small part of the image. So we did the same for patches. So here, patches of eye and the mouth. And actually, the conclusion is the same. So definitely, we say that GANs are not memorizing, pure GANs. Okay. So now we compare to FID. FID was the metric that is mostly used to assess the quality of GANs and the generative model in general. And by this figure, we demonstrate definitely that FID is not capable of detecting memorization. So here is the metric we propose. We can use the p-value of the KS test of the median recovery error. Here is the FID. So for the lowest is the better for FID because it's a distance. Okay, so the best methods are mesh-shader here and PG-GAN. DC-GAN is here. And GLOW, surprisingly, is quite close to DC-GAN here. And for GLOW, we show that if we train with a small number of images, we have definitely a gap in a recovery error that suggests overfitting, while the FID is exactly the same. So definitely, we propose a new metric which can assess the quality and the memorization. Okay, I don't know if I have time left. Do I have? Yeah. So it's not an in-depth study, but it's just to show that with this new insight and latent recovery, we can drive some new applications. So one which is straightforward is face de-identification. So there are papers devoting to that, and what we are saying is that we can take out-of-the-shelf very good generative model and use latent recovery to generate new face when using pure GAN. Okay, you can even get a dude here. Okay, but we can still enforce gender or stuff like that if you want. So another interesting application is super resolution. So this is a paper from ICCV 17 in which they try to compute the super resolution to improve the resolution of a small image. So they train a full hybrid GAN to do so. So this is the ground truth. This is what they get. And here is what we obtain by just using latent recovery with pooling. Okay. So we have exactly the same performance, except that we never train the network to do so. We just use it directly. The last application is phase completion. So there are two state-of-the-art approaches from last year and before, in which they train on the same dataset, but with hybrid GANs. And again, hybrid GANs may overfit the datasets. Okay? That when this paper came out, people have a lot of suspicion about, hey, is this method just copying what we have in pain? Because during training, we force the generative network to recopy what has been shown. Okay? So what we propose instead is to train a pure GAN approach and directly use the latent recovery. So here, without any tricks, like here, okay, there is no Poisson branding or anything, just out-of-the-shelf network. We just reconstruct the image given the border like this. Okay. So to conclude, we provided a new simple definition for overfitting for generative networks. We gave a simple algorithm to detect it. We proved that pure GANs are not overfitting, at least on the dataset we tried. And on the contrary, that hybrid GAN are prone to overfitting, which is very important. That raises a lot of problems with privacy. We also demonstrate that FID is not overfitting, do not detect overfitting, sorry. And we also investigate some application in which we can generate faces while preserving the privacy of the dataset. So there are interesting future work to do, like, for instance, trying to have a faster recovery. Instead of doing optimization, maybe we can train the network to do so. And actually, it works. We can try also to improve optimization because it works very well for phases because it's registered, but for other datasets, it still works, but it's not as nice. Okay, so definitely this is a very strong topic that I would like to further investigate. Thank you very much.
Thank you very much for your talk. There are some questions in the audience.
Do you explain the inpainting?
Can I explain the inpainting?
What you do the inpainting at the end?
Oh, it's okay.
Could you re-explain how you did last experiment?
I use this this equation. So phi here is a masking operator. So I try to generate the best image, provided only the value on the border, and that's and y here is the target image. That's it. Yeah.
Okay.
it's very simple.
I'm just wondering about the number of latent variables. So it's always the same?
Across different architectures, okay, it's not.
Yeah?
Yeah, for PG-GAN, it's the best we tried, generating those images. It's 44 millions of parameters. And for DC-GAN, it's about a few millions. And the training takes a day.
Yeah, but okay, because the Z, the dimension of Z.
Oh, Z, sorry. For DC-GAN, it's 128, and for PG-GAN, it's 512.
512. Okay, but these two numbers are very important because when you increase the number of latent variables, you can reproduce more or less everything. So there is something I don't understand in the fact that if you increase this dimension, more or less you could just imagine that you can generate everything. So at the end, you will say that you have no overfitting because in both cases, on the training set and on the test set, you can recover the image. So you will see no difference between the distances in the two sets, and you will deduce that you have no overfitting.
Yeah, if I have a generator that generates everything, yes, it's kind of okay.
Yeah,
that's a very good question because
because you know I can have a very stupid random network which is just I produce just arbitrary values for pixel and it will be able to reproduce any image.
Okay,
so you will say that I'm not doing any
does that actually. That's a very good question. Let me. Okay, this network, for instance, which is called GLOW, but with a W, it's an invertible network. So basically, it takes as an input an image and gives as an output another image. Okay, so we have the same parameters. So those are invertible, but yet they do not overfit. But I agree with you. If we can produce, if it's completely invertible, I should be able to generate an image so that it's yeah, it's cool. Yeah, I would say that if we have too much latent variables, training is very difficult. We need a large, very large test. It hasn't been done yet.
Try to estimate on something which is okay. You do it for faces, and after you work with bedrooms, and you just look if you can not do as well with bedrooms, for instance.
Yeah, we did test on bedrooms as well. But it was not, we didn't detect overfitting for pure GANs as well. But yeah, I agree with your point. Yeah.
Thank you for the presentation. I want to ask, have you tried to use for conditional GANs or just unconditional? It's with any input?
Conditional GANs?
Yeah.
No. The one we tried was the list I gave here, those ones. Yeah, there are tons of GANs. It's, but I would say I'm pretty confident that if the GANs is pure, meaning that we just have an adversarial loss, then you will not have overfitting. What we observe is that if we try to train those networks with few images, it completely fails. And one way to make this works, train with a few images, is actually to have L2 loss function somewhere. And then it's what we call hybrid GAN, and then that's overfitting.
Thanks for the talks. In the beginning, you showed like from like Goodfellow's 2014's work, like a couple of GANs after will be better, give better image. But later on, using your method, you said some good image, good result GAN actually has overfitting. So
actually, all those are not overfitting. It's quite deceiving, but those are pure GANs, a method that do not overfit.
Okay.
But I mean, it's the application of those is just to generate images. While in practice, we want to solve problem. So we want to, I don't know, to inpaint medical images or stuff like that. And for those kind of problems, people are using hybrid GANs that can overfit. So that's what we claim.
Okay, thank you. I think if there are some more questions, Julien will be around the whole week. So, yeah. Thanks again.
Thank you.